I will spend the 5 minutes for introducing the speaker. So, good morning, ladies and gentlemen. How are you? It's okay? Please sit for the seat because we have around 30 audience. So I think you are familiar with Professor Vladik Kreinovich. I shared with him at several conferences. I shared time with him. But I would like to introduce him briefly. As you know, his name is Russian origin. He studied at St. Petersburg University and obtained the bachelor and master degree. After that, he moved to Russian Science Academy and obtained his PhD degree. And he studied first mathematics and computer science. As I told, St. Petersburg University, a very beautiful city. And he obtained a master in 1974. So you can get his age. Not old, but not young. Nearly my age. And he obtained a PhD in mathematics. The Institute of Mathematics, Soviet Academy of, not the Russian, because at that time they used the Soviet Academy of Sciences, Novosibirsk, in 1979. And after then, he was with the Soviet Academy of Science for around 5 years. And after then, at that time, he worked on the special physical observatory problems. And he worked on the error estimation and intelligence information processing for the National Institute for Electrical Measuring Instrument. After then, in 1989, he was with the Stanford University and as a visiting scholar. And then in 1990, he moved to the present institute, the University of Texas at El Paso. As I told, I found him in various places, not only conferences, in journals and books. He already published 4 books and 10 edited books, and the 900 publications of papers. So his work is very fast. When I ask something, he's reviewed, written in 1 or 2 days. So the work proceeding can be reviewed in a very short time. As I thought, his work is very quick. So please follow his working style. So today he is he's very much concerned with fuzzy set. He has the very high position in IEEE society, and you can find his name also in IEEE. Maybe did you visit Beijing?
Yes.
This time. So several students may or not here. They graduated master. So five students attended there. So unfortunately I could not go there. So his title is Decision Making Under Interval and Fuzzy Uncertainty. Based on the utility approach. So thank you very much for coming here from very far place from the United States. Welcome.
Many thanks for the great introduction and for all the kind words. It's definitely my pleasure to be here. This is my third visit to Japan, and I always enjoy Japan. It's such a nice country with lots of art. Is there a microphone? Ah, do you need a microphone?
Yeah, I know.
Okay.
The voice is very loud.
Okay.
Yeah. Okay. Do you have a pointer? Yes, I have.
Okay. Okay, so this is the general talk on decision making, on the interval and fuzzy approach, utility, on the uncertainty utility approach. Oh, okay. Okay, excellent. Let me try. Yep. Okay. Okay, sorry. Okay. Okay, so let me first explain what is utility and why utility approach. In fuzzy community and overall in general in uncertainty community, tradition is people say, oh, utility, everybody knows it doesn't work, it's wrong. And my goal is to explain what is utility, how to use it, and actually that it's not so wrong as sometimes it's claimed to be, and it's actually very helpful. So, it disappears. Second alternative is very good. Everybody becomes a millionaire. Okay? So that any real alternatives which we select is better than A sub 0 and worse than A sub 1. There is a textbook by John Isbell in which he tries to, on game theory, in which he makes it a very extreme. A0 is I'm being burned alive in oil, and A1 I'm kind of immortal, I'm God, I'm living in paradise, and so on. This is extreme, but we can have that. And so what we can do is very simple. For every number p from the interval, that all possible utility values are between this product and this product, then we apply the same Hurwitz criteria, and we get what? This possible value with probability alpha h, and this negative value is probability 1 minus alpha. And these values are different. So, in other words, additional information decreases utility. And this is like what the good book says, or with much wisdom comes much sorrow. So if we don't know where everything comes from, we may become too optimistic. In reality, usually we're a little bit more realistic if we know the details. So, what happens if we go beyond interval uncertainty? What do we mean beyond interval uncertainty? So, in addition to the intervals, we may have some partial information about the probabilities of different values from this interval. How do we describe this partial information? Let's go back to the main question. How do we describe an exact probability distribution. And there are many ways to describe it. We can describe it by moments, we can describe it by probability distribution function, by cumulative distribution function. And a partial information is we have a class of possible cumulative distribution functions. And so what does it mean we have a class? It means for each value z, instead of knowing the exact probability, which is the cumulative distribution function, what we know is maybe bounds on this interval. If we have very little knowledge, then these bounds are what? Probability is in between 0 and 1. These bounds are 0 and 1. This is something that is called a probability box, or for short a p-box, a concept introduced by Professor Scott Ferguson. So in this case, what is a p-box? For every z, we know an interval of possible values of f of z. Now, this is kind of a heuristic. What should we do in general? In general, we should look into our goal. Remember, the goal is to make a decision. And we make a decision based on the fact that the expected value of the utility is the largest. So now, we should select the way to represent a probability distribution in such a way as to help us make this decision. How do we do that? Well, let's consider two cases. The most usual case is the smooth utility function. For example, if we're talking about finance, if we're talking about most other situations, if we increase the value a little bit, utility changes a little bit, right? So, what we have here is a function is smooth. Smooth means what? We can expand it in Taylor series and keep, if the value is approximately known, keep only the few first terms in this expansion. And then the expected value will be what? The expected value is a combination of expected value of x minus x0, x minus x0 square, and so on. The expected values are the moments of this distribution. So we need to know the moments. And in this case, that to describe uncertainty, we describe interval bounds on the moment. Case 2 is when we have a threshold type. For example, usually in like environmental things, right? What is environmental thing? It's like there's a famous joke, but I think it is true. I hope you all like to eat at McDonald's, right? My former chair shocked me when first we came to the United States by saying, do you know that at McDonald's they're required to have no more than one red dropping per several thousand pieces of meat, right? It's maybe a joke, but you have to have some limitations. Same thing, a factory cannot emit more than certain number of parts per million of some chemicals into the air. Means what? If you have exactly one red dropping per 1,000 hamburgers, you're okay. If we have 2 red droppings, that's it, big fines, your restaurant is closed or your company is getting a big fine. So here, the utility has a threshold in case of regulation, or speed limit. What is a speed limit? That's exactly this, right? If the speed limit is 100 kilometers per hour, if you drive 99, you're okay. If you drive 100, you're okay. If you drive 105, the policeman will stop you and fine you. In Japan, I think it's even more so, right? Okay, so in this case, when you have a threshold, what we actually have is utility jumps immediately. And so the expected value is proportional to the probability of this jump. And so what we have is we have a cumulative distribution function, and then uncertainty means we don't know this value, so we use the p-box. Now, I'm going even further. What if the interval values are difficult to explain? And I'll give you one specific example on which we worked. It's a selection, and then I'll go back to general decision making. Selecting a location for meteorological tower. Let me explain what we have. So, in the old days, weather prediction was kind of a joke, because the statistician would notice that if you just flip the coin, you predict the weather better than the computer models. Now, in most cases, weather prediction is reasonably good. It's still difficult to predict where the tornado will go or something else, but in normal weather, it's definitely much better. Why is it not perfect? The equations are well known. The big problem is we need the input data, because the equation, they tell you if this is the temperature now, then that is what will be the temperature in the future. And so to get more data, we have satellite data, we have sensors everywhere. It's usually much better in the big city because you have a lot of people who volunteer to be part of what is called weather underground. They put sensors outside, they combine that, but in the remote area, it's a big problem. It's a big problem. You need to know not only too close to the road, then what you're measuring, for example, in terms of CO2 and other gases, you're not measuring the natural thing, you're measuring the gases from the cars driving on that road. If you build it too far from the road, then you will have, because there's no road, so how do you build this tower? You have to carry everything yourself. We actually participated a little bit in carrying. Ours was like 100 meters away from the road. And let me tell you, it's heavy. Okay? It's complicated. So, let's see how this works and what we can do in this situation. So we have several criteria, and I already mentioned one criteria about the cars. Another is inclination. It's nice if you have a flat area, but in many cases it's inclined. So if you build it an inclination that is not typical for this area, all the gases will just go down, and you will enjoy, like if you measure the air quality on the top of the hill, of course it's good. But in the valley, it may be awful. On the other hand, if you measure in the valley, that's also bad. So always there is need to be to combine different criteria. How do you select that? So we have differences which have to be non-negative. So the distance from the road has to be positive, the maximum might be positive, and so on. For each difference, the larger the value, the better, but they are in complicated situations. So what we have is a so-called multi-criteria problem. When we have several criteria that we want to satisfy, and we don't know which weight to assign to each one. Traditionally, these problems are solved in a very simple way. If we don't know which, so what do? We assign some weights, subjectively or whatever it is, and we select an alternative for which the weighted average is the largest possible. This is a very typical approach in economics, in everything. We don't know, so we give some weights, and then maybe we vary these weights to see where everything goes. But what we want is, we want something that is scale invariant. Let me explain. So each alternative is characterized by a tuple of possible values. So we have a tuple of a set of tuples of possible numbers. And for each two alternatives, we want to know either that y is better than y prime or y prime is better, because we want to select a single alternative. Of course, natural requirement is it should be transitive, and so we get a total order. Now, what we want from this total order, we want if each criterion is better, then the alternative is better. So if each value is larger, then y should be better. And since we need scale invariant, what does it mean, scale invariant? As I mentioned, the quantities describe completely different physical notions measured in different units. For example, wind velocity could be in meters per second, miles per hour, and so on. Elevations could be in meters, feet, and kilometers. And we don't know which units match each other. So ideally, we should be able to change these units without changing our criteria. So if we simply change the unit, the relations should not change. What does it mean that we change the unit? Changing the unit means what? Replacing each value with the value multiplied by a constant. So for example, if we start with meters and go to centimeters, that means what? We're multiplying everything by a factor of 100. We can use any other units. And so this criterion in mathematical terms comes to the following. If one vector, we want to have the ordering relation in such a way that if this vector is greater than that one, then if we multiply each by the corresponding parameter, so we rescale the first value by lambda 1, the second by lambda 2, and the nth by lambda sub n, we should still have the same ordering relation. And same thing with equivalence. So now we can have a precise mathematical problem. So we have an ordering relation. It should be non-trivial, which means we should have some which are better than the others. It should be monotonic. If the values are better, all the parameters are better, then it should be better. It should be continuous, which makes perfect sense. and it should be scale invariant. And this is the result. Each non-trivial monotonic scale invariant continuous closure have the following form. So what we do is we take the products of the values raised to some powers alpha sub I, and we select the one for which this product is the best. That's how we select the towers, and that's, as we learned out before, that's how NASA selected the place for landing for the Apollo mission. Because what happens is, now we know a lot about the moon. In the old days, before that, people didn't know much about the moon, so how do you select the place? We want the place which is easier to get, but we want the place which is more interesting from the viewpoint of science. So if you land on the complete flat, it may be the easiest, but if you land near the crater, it might be more interesting to analyze and so on. And vice versa for each values alpha, these formulas describe the corresponding self-invariant criteria. So conclusion is, what is the practical conclusion? If we need to select an alternative, each alternative is characterized by some non-negative parameters. If you have this additional restriction of non-negativity, then instead of selecting an alternative with the largest weighted combination, what we should do is we should have an alternative for the largest value of the product, or equivalently, we take logarithms and combine them with the corresponding weights. How is it related to decision making? In general, until now, we considered decision making when we have one agent who makes a decision. But as I mentioned, decision theory started not with the theory of one agent, but with the theory of game theory. When you have a complex situation, when you have several people with different preferences, and we need to coordinate, we need to combine the interests of all of them. So, how do we do that? And we're not talking about what is called zero-sum games, where either I win or you lose, because these are rare. These are usually artificial. In most cases, we have a possibility of collaboration. Even in the old days, when the two, well, maybe I'm just using my Marxist education, when the two feudals were fighting, right? Is it 0-1 game? No, because what they want, the proper solution is, what they want is, they're fighting for honor, for whatever it is, but in reality, economically, they're fighting for the right to get the income from the peasants of this area, right? So of course, it's not a zero-sum game, because ideally, they make an agreement and they divide this area between themselves. This is called peace, right? These peasants bring their food to me, these peasants bring their food to you, and we have peace, we don't kill each other. Okay? So, here, for each participant, we can determine the utility for this participant I of alternative J. So what we want is transform these utilities into the reasonable group decision-making rule. And this is the area, I mean, it's like teaching decision-making, it's more like, I don't know. In computer science, we don't have that, but like in physics, very few people who teach physics can say, well, when I was younger, I remember Newton told me, right? Or Einstein told me. But here, we can refer to people, many people who have contributed to decision-making. They're still alive. You may see them at the conferences and everything. Same thing with computer science. So there's another person, and many of you know the name John Nash. He became famous through the movie The Beautiful Mind, because he was crazy. I mean, most of the scientists are not exactly very normal, but he was really certifiably crazy. But he was a genius. Like, he got a Nobel Prize after all. And this is not related to his most well-known things. He did a lot of interesting things. This is something called Nash cooperative solution. So what we do is, because each utility is determined modular an equivalence. And if we have a status quo situation, that is the situation we have now, right? So we fix the starting point, but we can still have different units. And units corresponding to different decision makers are not related. How much time do I have? Till 11:30 or?
I think it is not necessary for you to care about the 4 minutes.
4 minutes. Oh,
yeah.
Okay.
But you can extend. How many minutes do you need?
Well, maybe 10 more.
Okay, it's okay.
Okay.
Just shorten the break.
Okay. 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 So we have the same formula as before. So now we have scale invariance, right? And because of the scale invariance of each alternative, we have, as before, the same formula with the product. But now we can have an additional criterion. An additional criterion is that we have we assume that all agents are equivalent. We don't want to create a favorable treatment of that. So that means all the weights are equal, and therefore maximizing this product is equivalent to simply maximizing the product of the utility. This is called Nash's bargaining solution. And this is what should be decided, and that's how decision making should be made in the situation when we have several alternatives. The interesting thing is Nash's solution can be easily explained in terms of fuzzy logic. Because what does it mean? We want all participants to be happy. So we want the first participant to be happy and the second to be happy and so on. Each utility describes the degree of happiness of the participant. And to formalize and, we can use, for example, the product, one of the simplest operations proposed by Zade. In this case, the overall degree of happiness is simply the product. This is not the proof of Nash's theorem, but what it shows is that Nash's result is very intuitive. It fits very well with our intuitive understanding of what we want. It's not just a mathematical paradigm. In case of intervals, correspondingly, we have the product of the utilities, so we can have we can replace this, for example, with the correspondingly Hurwitz values, and we get this out. Now, here we end up with a very interesting thing. So there's a so-called arrows in possibilities. Again, this is another person who got a Nobel Prize, Kenneth Arrow. He got Nobel Prize in 1972, one of the first, and he published his paper in approximately the same time in 1951. What he showed is the following. Suppose that we have a group of participants and we need to select one of the alternatives. So to select and to find individual preferences, we ask each participant to rank the alternatives. And based on n rankings, we need to find one good ranking. And so what he proved is that this is not possible. So either if we have two people, then it's easy. If we have two alternatives, it's easy. We just select A1 if majority prefers A1 or A2 if majority prefers A2. That's what voting is about. But if we have three or more alternatives, then it becomes a big mess. If we cannot have, if the group, the only way to make things that satisfy these reasonable conditions is what is called the dictatorship. If we have one person who makes a decision. It often happens if you have like a group of students. When I was a student, we have a group of students and we want to know where to go to have a snack after the classes or maybe a drink, right? What happens normally? Everybody starts arguing and we spend time. So the good idea is to have one leader who will say, okay, guys, let's go to this place. Okay? To have shish kebab. Okay. So now how to solve this problem? To solve this problem is very simple. What Arrow says is that we only have binary preferences. We cannot make the decision. But in reality, the preferences are not binary. We need to take into account degree of preference, which means, and how do we describe that? We describe that in terms of utility. And if we have utilities, then what we do is we can find for each solution the corresponding Nash's bargaining solution, and we have something that is actually unique, it can be proven, and which provides the way to avoid Arrow's paradox. So you can make group decisions without having paradox. Now, all these things assumes that we are all open to each other. We are telling each other what we want. If you read newspapers, politics is not about telling what you want, right? Like China says, well, Abe says this, but what he wants is control over the whole Asia. On the other hand, if you read papers about China, they say, well, they say they want peace. In reality, what they want to install communism on the whole world and so on. So how do we tell? Of course, sometimes it's easier to cheat. It's beneficial. And if you cheat, sometimes you can force the group to select the better alternative. I'll skip this mathematics, but I think it's common sense and you can guess what I have in mind. But the good news is that cheating is, in general, not very beneficial. So if people don't know each other's utilities, then if we use the criteria of Nash, then it turns out that cheating is not beneficial. The best way is to open the solution. And here is a very specific example, territorial division. I wish it was as easy in real life as it is in game theory, but in game theory has been considering this problem for a while. Suppose you have a territory that is disputed between several states or several feudals or whatever it is. Then instead of fighting, what you can do is you can estimate utility and then maximize the corresponding product. And there are simple, well, not simple, but there are algorithms for deciding this, solving this optimization problem. And there is a theorem which says that if you submit false utilities, then in general you may lose in this game. So it's easier, this is the alternative. So when alpha is positive, then the maximum value of this criteria is the largest when you plug in your actual utility function. So it's beneficial to tell the truth about your preference. You may not tell the truth about everything else, but at least you need to let people know what you want. Now there's an interesting another problem here, which is, suppose you have a group of participants who are teamed together and you are kind of always getting together and they don't want to reveal their individual preference. For example, you have a political group, whether it's a political party, sometimes in the open, but most times they the cliques, they check together and they try to hide their differences, they act as one person. Is it possible to determine their individual views? And this is actually possible if the group uses Nash's bargaining solution. So what happens from a mathematical viewpoint, so what does it mean? It means that we need to find their utilities in such a way for each two alternatives, for each two possible lotteries. We have this order, and we don't know utilities user by j. It turns out that these utilities can be uniquely determined based on this solution. So if you have the group, so this is the problem that in the old days, so-called Kremlinologists used to analyze. So sometimes some decision comes from Moscow. They know there are different people in Politburo have different opinions. This time they try to do that in China, try to do it with Al-Qaeda and so on. Okay? And finally, just to finish off on a little bit more positive thing, instead of wars and conflicts, about this. One of the problems with utility approach is that utility is a very perceived as something very egoistic. Utility means I get more. I get more, I'm happy. And that everybody else gets less, let them suffer. In reality, of course, people care about others. That's a very natural thing. And it can be taken into account in the utility. Namely, the degree of person happiness depends on the happiness of others. Sometimes the dependence is positive, sometimes the dependence is negative. They're jealous, right? There's a joke in Russia, but probably has existed in other countries, like God comes to a peasant and says, well, since you were so good and you always kind of didn't do anything wrong, I can give you whatever you want. Just make it happen. And the peasant says, well, you know what? Don't give me anything. Just destroy the farm of my neighbor. I hate him. Okay? So that's not a good thing, but it happens. And so again, we're talking about different Nobel Prize winner. Very simple formula, still got a Nobel Prize, Gary Becker. So what you do is, if you have utilities of other people, so this is utility that doesn't take into account interdependence based on only your income, but your utility is equal to this one plus a linear combination of utilities of other people. Sounds very simple, you may be yawning already, but let me explain why it's not simple and why we get into problems here. It's called paradox of love, or in Baker's paper it was paradox of Romeo and Juliet. So you have two people who are madly in love with each other. Okay? So U1, utility of Romeo, is what he gains plus what Juliet gains times some coefficient alpha 1. The utility of Juliet is what she gained plus what Romeo gains. So you have a system of two linear equations, two unknowns, very simple to solve. Here is a solution. Why is it a problem? The problem is if the product of alpha 1, 2 and alpha 2, 1 is greater than 1, as in the case of Romeo and Juliet, then what happens? This becomes negative. So when two people are deeply in love, then original pleasures may lead to unhappiness. That's exactly what happened to Romeo and Juliet. So the proper solution is, again, in Russia we have this saying that in the happy family, usually one person loves and the other allows him or herself to be loved. That's probably the best arrangement from the viewpoint of decision making theory, as opposed to everybody loves too deeply. If everybody loves too deeply, you get shootings, you get killings, you get Othello, you get God knows what. Now, another problem is, why not have three? I mean, okay, so God said you should have one wife, and some gods said, no, you can have two wives, you can have three wives. What's wrong with having several people living happily together as opposed to the husband and wife? And again, from the viewpoint of decision making, what happens? Again, let's consider the same situation. Suppose you have this 1 minus epsilon, which is guaranteed happiness for the case of the couple. For two people, we're okay. For three people, we already have unhappiness. So corollary, if you have three people living together, it's good to have a little bit of negative feelings, otherwise something is wrong. So it's kind of biologically and psychologically inclined. I don't know if you have that. Person lives with his mother and his wife, it's okay to have some jealousy between them. It helps to avoid different paradoxes. Now, another way, promoted by another Nobel Prize winner, is the following. He said, okay, what is the problem here? The problem is, why do we have this increase? The problem is we are dealing with emotions. The good way is, the proper way is to ignore the emotions and to think about the good quality of life. So, if you truly love your children, you should not care to their whim. You should not listen to when they cry when they not. You want them to have a good life. You want them to have good education. If they cry once in a while, tough, life is tough. This is called tough love. In case of the tough love, promoted by Amartya Sen, there is no paradoxes, there is no everything. Everything is perfect, and we have a very good decision making. Okay? So thank you very much. If you're interested, I have about an hour more, but I think coffee break is definitely important. Your utility will be increased if you have a coffee break.
So, thank you very much, Professor Kreinovich. Yeah, we have still time. We may shorten our lifetime. So we would like to accept several questions. Do you have any questions?
You better ask.
Okay. Why don't you use the microphone?
Thank you, Professor. I think your topic is very interesting. And in your early pages, you mentioned the bisection. I have a quick question about the bisection. And you mentioned that the number of bisection is n case power of 2.
No. What I'm saying is that if you have k steps in bisection, you divide the original interval into 2 to the power. You decrease the size of the original interval to 2 to the power minus k.
Okay.
So when you have, good question.
So the growth is not exponentially.
No, the decrease is exponential.
Oh, okay. So the decrease is very fast.
Oh yeah. Okay, I'll show you. So it should be Yes, here. So right. So what we have in one step. So we start with the interval 0, 1.
Okay.
After one equation, about 0.5, you get either 0 to 0.5 or 0.5 to 1. Then if it's 0 to 0.5, you ask a question about 0.25, about the midpoint. And you immediately get an interval of size 1/4. In 3 equations, you have 1/8 and so on.
So the bisection is effective.
bisection is a very useful tool in like root finding. I mean, it's not as efficient as, for example, Newton's method. But with Newton's method, we need to know derivatives and everything. This is kind of a sure-proof way to find the root of the function and to find the optimal value.
Thank you for your next question. How about the questions? I have some questions and 20. Next one. You calculate the probability at some place before you use the summation, the lower and upper probability. So you calculated the probability, total probability using the upper probability and the lower probability.
UNB.
Okay.
So I wonder.
One second. So, yes.
Where such a calculation, like this, where such a calculation
comes from?
Keep the total equal 1.
Oh,
is it
no, but they are not
sure?
Yes, because if they are not.
Total this one total equal 1.
Yes.
Will not,
So
you don't care about the probability should be the total equal 1.
No, because we, if we know, that's a very good point, and that
so
needs to be analyzed.
You deduct the some condition.
Right. So if this is assuming that there is always some, I should have mentioned that, but thanks a lot for mentioning, right. This is assuming that we have possible outcomes, but it's always possible to kind of do nothing or nothing will happen. In this case, we don't care. But if we do care, then yes, these formulas need to be modified because then we are no longer considering all possible values of the probabilities. We're only considering additional constraints.
Right.
And then instead of this thing, we have to maximize not just this probability, but this probability under the constraint, which leads to different results. Yes, absolutely.
Okay, thank you. You have other questions? Please. I don't need the microphone. I know your voice is quite
Thank you, Professor. In decision making, marginal utility as a function has become even more important today because with every utility consumed, marginal component of it, the utility factor reduces. Don't you think you may want to advance your model to look at marginal utility and consume it from the decision making process?
Well, but I mean, this, I'm just more, you're absolutely right. In terms of when it comes to the actual algorithms for producing decision making, you have to modify it. But this, I'm just trying to lay out the foundations. So, yes, when it comes to the actual decision making, there is a lot of way to doing the algorithms, and marginal utility is one of them because basically you are, instead of just considering everything from scratch, you are describing, and it's much more efficient way to do that. Instead of considering everything from scratch every time, you only consider how things changed. And that's definitely a much easier and much more efficient ways to deal with that. You're absolutely right. So yeah, maybe that prompts the whole statement that this is, God forbid, not the whole decision theory. If you Google, you will see decision theory, like tons of books and everything. And my purpose here is how to introduce uncertainty, interval and fuzzy uncertainty, into the decision theory. So what I was doing, I was just talking about things, many of them go back to 1950s, and show how interval uncertainty can be incorporated. But yes, definitely, this is like the whole area of research. And traditionally, in most cases, especially in economics, decisions are made based on the probabilistic theory, where you make an assumption that you know everything. And that's one of the supposed reasons of sometimes problems, because if you assume, for example, the distribution, you assume it's Gaussian, it's not Gaussian. As a result, you get problems with economics, with finance. Like many newspapers blamed mathematical methods on the 2009 big decrease in stock market on the economic methods, and to some extent they're right, because if you assume the distribution is Gaussian, you think huge deviations are rare. In reality, it's a power law, and so that's a big problem. And so this may help, this approach may help to solve these type of problems.
Okay. Thank you very much, Professor Agarwal. How about other questions? Do you like to have any question? Okay, thank you very much, Professor Kreinovich. I have one more question.
Okay.
Do you open this slide for the conference? This slide?
Yeah.
In PDF. Is it possible?
Sorry?
Can you use this slide for us?
Yeah, sure.
Is it okay?
Yeah,
and
yeah,
also
absolutely.
the Professor Agarwal take a video of
Okay.
you talking.
Thank you.
Is it possible?
Sure, absolutely. No, I'll
to
be
use this video.
sure. I'll be
Can
delighted.
we open? There are several.
These
levels.
slides are already on my website, so they are open for everybody.
I see.
I put